So now it's recording. This is the written homework for week 6. We're going to go over the written homework for the first hour, and then hopefully for the second hour we'll have time to do the online homework as well. So I'm going to reshare the screen again here, and then we can go ahead and pretty much get started. So share, okay. And let me know again if that's if you guys can see that. Okay, cool. Alrighty, so with this homework, we have a lot of the centripetal acceleration, centripetal force type problems, right? So first of all, we have twisty road. The car in the diagram below travels at a constant speed along the road as shown, right? So part A is asking us to draw vectors showing its acceleration at points A, B, and C, and if any of the acceleration vectors are 0, we write that acceleration is equal to 0. So let me actually hit do not disturb first here so don't get any notifications. All right, so vectors for A, B, and C indicating, oh, it looks like it's blurry. Okay, one sec. Let me reshare that. Sorry about that. Hopefully now it looks better. One sec here. Trying to make sure that everything. Okay. Sorry about the hold up here. I don't know what's going on with this. Blurry again. Okay. One sec. Okay, let's try this. Is it looking all right now? I really hope it does. Looks good? Okay, cool. Sorry about that. Okay, so got that out of our system. So we have to draw vectors showing the acceleration of points A, B, and C. If any of the acceleration vectors are 0, write A equals 0. So we know with centripetal acceleration, centripetal forces, right, what does that mean? That means for centripetal acceleration, we're going to have an acceleration that is directed radially inward, so towards kind of like the middle of a circle that we can perceive here, if we're traveling along kind of like a circular path. So for example, if we're traveling along this circular pathway here, right, along A, for example, this little trajectory here, this path is a little bit circular, right? So we can assume then that our acceleration vector at point A, for example, is going to be pointing radially inward like this, right? And that makes sense because for centripetal acceleration, it's always, that's why they call it centripetal, like centripetal, right? So it's going to be pointing towards the center of the circle, right? So if we were to think about this as kind of a circle, this little trajectory here, this point, the centripetal acceleration, we pointing towards the middle, right? Now, how about B? Are we traveling along this trajectory here? Are we traveling along kind of like a curved pathway, or is it relatively straight? Pretty straight, right? So that means that our acceleration vector along part B, right? Normally, if there's an acceleration, right, if we're speeding up, for example, we would have an acceleration be pretty much in the same direction if we're speeding up as the velocity, right? Or if we're slowing down, for example, it would be opposite to it. Now, thing is here, the car is traveling at a constant speed, right? So if you're traveling at a constant speed, you're not really changing your speed, right? So you're traveling at a constant 30 meters per second, 30 meters per second at every single time interval, right? So if you're not changing that speed, then technically you don't even have an acceleration. Because if you think about it, acceleration, as we learned in the first couple of units, is that acceleration kind of comes in two flavors. You can either have a change in direction causing that acceleration, so acceleration by change in direction, right? Or we can have an acceleration by speeding up, slowing down, so like changing the magnitude basically of our speed. So if we go from 30, 40, 50 meters per second then we're speeding up, right? We're increasing our velocity, increasing our speed, whatever it is. And then we could also, for example, like at point A here, we're still traveling at constant speed everywhere. It's just that now we're changing our direction. We went from maybe like northeast here to just east, and now like south, east, whatever, right? So for A, at point A, there's a change in direction basically because of that curved pathway, which causes there to be a centripetal acceleration. Point B, since we're traveling along this just constant linear path right there, we shouldn't have any acceleration because we're still traveling at constant speed. There is no change in direction, and we're not speeding up or slowing down because it's at constant speed. So at point B, neither of these conditions help us find an acceleration at point B. So at point B, there should be an acceleration of 0. And at point C, since it's also a curved pathway, right, we should have a centripetal acceleration pointing upwards, right, towards the center of the circle. So if the circle was like this, right, you wouldn't have your centripetal acceleration pointing outside of the circle. It'd have to be radially inward towards the middle of the circle, towards the center centripetal, right? So that's your vectors for part A. Now for part B, we have to rank the magnitude of the acceleration at the 3 points. Now, for part B, we can really see, well, okay, well, if A has a vector and C has a vector and B doesn't even have an acceleration, right? So it logically makes sense for B to be the least, or have the least magnitude of the acceleration for all those 3 points, right? Now, how do we compare A and C? Anyone have any ideas? Radius, excellent. So since we're traveling along, with a constant speed, right? So V is the same for everything, right? Now, what isn't the same is the fact that our curvature here is different, right? This is a larger circle that we can imagine here versus maybe a smaller circle that we can imagine here, right? So the radii are going to be different. So if we go back to the definition of what centripetal acceleration is, right, we know that's v squared over r. Well, if v is the same, if we're traveling at constant speed, and radius is different, right, because this, for example, this to the center here is about this length, and then maybe from the center there is about that length, right? So the lengths there are different for the radii, right? So if you have one radius bigger than the other, that's going to differ or cause a difference in the acceleration, right? So in that case, which one has the larger radius? It would have to be at point A, right? Because this length here is a lot bigger, this radius is a lot bigger, this curvature, right, is a lot wider. It's a less sharp of a turn as opposed to this one. So if radius is bigger here, right, what does that do to the acceleration value or magnitude? Yeah, so it makes it smaller, right? As opposed to, so for example, if you were to think about this as fractions, for example, right? If you had, your velocity was 1 on the top, v squared was equal to 1, and radius was equal to 2, so 1/2 versus maybe 1/3, right? You can see that this is 0.5 and this is 0.33333, right? So if you make the radius bigger, you decrease the acceleration, right? So you can also think about it as if you're taking a sharp turn, right, on the road. So if you're making a really wide turn, you don't really have to like go as fast to make that wide turn, right? Now, if you're making a really sharp turn, you might have to go a little bit faster to kind of whip the car in that direction, right? And so you'd have to have a larger centripetal acceleration, basically. So in that case, since the radius of curvature is bigger for A, it means a smaller centripetal acceleration. So that means B is the least, because obviously B doesn't even have an acceleration, then A, then C. Because C has that smaller radius, right? And that means it has a larger acceleration. Does that make sense for part B? Cool. All right. Part C, the road is wet with rain, and the driver is worried about sliding off the road. The driver decides to change their speed going into each turn so that the centripetal acceleration is the same in each turn. When the driver is approaching the second turn containing point C, should they be going faster or slower than they were in the first turn containing point A? So normally, right, in the beginning of the problem, we had that everything is traveling at constant speed. This is 20 meters per second, right here's 20 meters per second, right here's 20, here's 20, right? Now, because you have this difference in curvature, right, this difference in curvature will alone cause a difference in the acceleration or centripetal acceleration vector, right, in magnitude. So if the driver's worried about slipping off the road, they have to change their speed, right? Because if they're They might be going too fast, for example, right? If, let's say, yeah, if they're traveling here with a certain speed, right, at this larger radius, well, they're going to have lower acceleration. If they travel with the same speed, right, with that smaller radius, they will have a greater acceleration. So there's a risk there of them like crashing or something or getting into an accident because they're traveling too fast. So if they want the centripetal acceleration to be the same in each turn, right, then we have to change the speed somehow to overcome the difference in the radius, right? So if the radius is bigger for this one and it's smaller for this one, for C, right? So if A is bigger than C for its radius, then we would have to try and figure out a way to equate the two centripetal accelerations, or centripetal acceleration magnitude values, right? So if, let's say, I don't know, if this is A and this is C, right? And if we were going by just normal ratios, I'm trying to just use numbers to kind of set this up in a way that's a little bit easier to understand. So if this was 3 on the bottom here, this is, let's do 3 centimeters or 3 meters is our radius for A, and 2 is the one for C, right? Let's say you're traveling at 1 meter per second or 1 mile per hour or whatever it is. We're just making up numbers here just to kind of, make things easy, I guess, with numbers. Anyway, so if we have 1/3 here, if we want to make this equal to 1/3, right, then what do we have to do to the velocity? Or to the speed, I mean. Because if you can see here, like if you travel at 1, well, we already said this is going to be like 0.333, and this is going to be 0.5. Or 0.5, sorry. So if we want to decrease the acceleration, how do we do that? To bring it down from 0.5 to 0.333, for example. Any ideas? Increase what exactly? So if we increase velocity, let's say if we go from 1/3 to, well, I guess if we go from 1 to 2, for example, well, you just upped it to 1. Well, if we're saying that if they were traveling at the same speed, this is 0.333 and this is 0.5, right? So if I increase speed from 1 to 2, for example, well, then it's 1. So what would I need to do to bring it down to this value? Exactly, right? So I'd have to bring the velocity down. We don't have to come up with a value or anything. This is just all like variables and understanding. I'm just using numbers, so maybe it'll look a little bit kind of easier. But basically, you'd have to go slower, right, to ensure that the centripetal acceleration is the same. So at point C, the person has to be going slower than they were in the first turn. So must go slower, right, to have the same centripetal acceleration, right? And that kind of makes sense in real life, right? So if I have that really wide turn at a certain speed, right? If I want to have the same centripetal acceleration, if I want to simulate that gradual turn with a really tight turn, well, if I go really, really fast, I'm going to just kind of like move around in the car and whip really fast, right? So if I want to decrease that jaggedy, raggedy movement, right, I'm going to have to go a little bit slower and kind of almost kind of expand or take my time basically through the turn in order to have that same centripetal acceleration. That's kind of a real world type way of thinking of it. But in terms of equations, right, for v squared over r, since a has a larger r and c has a smaller r, then we would have to decrease v, because that's the only other variable in play, right? That's the only other variable in play. So if r for a is bigger than r for c, then v for c has to decrease in order to keep the values the same. Does that make sense? All right, I got one yes. Is that good for everyone else as well? Okay. Cool. Alrighty. So we're going to move on to problem 2 now. Problem 2 is a car on a hill. So we have a 1,300 kilogram car coasts over the top of a circular hill at constant speed, right? Part A is asking us which free body diagram best represents this. Explain how you know. So this car right here is traveling over a circular path, right? So if we have a circular pathway, what does that indicate? What should we have? Exactly, right? So we should have a centripetal acceleration. So centripetal acceleration, right, if we're thinking about this as kind of a circle, right, it should point inwards, right, radially inwards. So there should be a force offering centripetal acceleration pointing towards the middle here. What do you think that force is going to be? If we just have a car kind of coasting on this hill, right, what do you think is going to offer that centripetal acceleration in that case? Gravity, right? Absolutely. So we have gravity, right? And since we're in contact with the road or something, right, what other force should we have, you think? Normal force, right? So normal force. Now, this is just me roughly kind of making things up here, right? So if we are supposed to have a centripetal acceleration, right? If we're supposed to have a net centripetal force downwards here, right? Because if we have, remember, for F equals ma, if there's an acceleration, the direction of that acceleration, right, will determine the net force. So if A, for example, is positive, then we have a positive net force. If A is negative, then we have a negative net force, right? So A here, we know that there's a centripetal acceleration has to be pointing radially inward towards the middle of the circle. If A is pointed downwards here, what does that mean for the force? For the net force, that is. Exactly. So we should have a net force, and that should be negative. Absolutely, right? So our net force should be negative because there's a centripetal acceleration. That centripetal acceleration is pointing downwards, that in the negative y direction, right? So A is negative, right? If A is negative, right, this is AC, by the way. If A is negative, then that means for F net is equal to MAC, for example. Then if that A is negative, we have a negative F net, right? So that means if we have a negative net force, or a net force in the negative direction, then that force should overwhelm the other forces in the y direction. So in that case, which one do you think is going to be depicting an overall net negative force? C, right? Absolutely. So C, because you can see here that this force here is a lot larger than the one in the positive y direction. This one is about equal, and this one has a positive net force. So we're trying to go by which one is going to offer us a centripetal force, a force that is going to allow us to kind of traverse that circular path. So if we have a centripetal force, right, centripetal force is going to offer a centripetal acceleration. If there's a centripetal acceleration, then the net force has to be in the direction that is radially inward, that same direction as our centripetal acceleration. So in that case, whatever force is offering that centripetal force, whatever force is offering that centripetal acceleration, then our net force has to be in that direction. So in that case, Fg, the force that is pointing downwards, the force that is offering the centripetal acceleration, the force that is the centripetal force, the one that is pointing radially inward, is going to be the one that has to overwhelm the other forces. So if normal force is pointing upwards like this, Fg has to be greater so that there's a negative net force, or a net force pointing downwards basically along the negative y-axis, that is going to be offering that negative centripetal acceleration, pulling us kind of radially inward, allowing us to traverse that circular path. Does that make sense? Cool. For part B then, actually I'll just write real quick. So if net force is downward or radially inward, right, due to centripetal acceleration, right? Then downward force has to be greater than the upward force. So Fg is greater than Fn in this case. But yeah. For part B, if the car has a speed of 30 meters per second and the hill has a radius of curvature of 120 meters, what is centripetal acceleration? So we know that centripetal acceleration is equal to v squared over r, right? So in this case, we have to also factor in the fact that they're asking for the centripetal acceleration and not the magnitude of the centripetal acceleration. So if we know that centripetal acceleration is pointing radially inward, so it's along the negative y-axis in this case, right, then our centripetal acceleration has to be negative, actually. So we should add a little negative sign here on the outside. So in that case, we have negative 30 meters per second, which is our speed. We square that, divided by our radius of curvature was 120 meters, and then we should get somewhere around like negative 7.5 meters per second squared. And it has to be this negative here because it indicates that there's a negative centripetal acceleration. There's a centripetal acceleration pointing along the negative y-axis, giving us a negative centripetal force, negative net force. So this answer has to be negative because they're not asking for magnitude. They're just asking for the centripetal acceleration. So they're wanting you to include direction in this case. This is the type of stuff that's implicit, right? If they're not asking for magnitude, it's pretty safe to assume that they're asking to include some kind of direction. But yeah, makes sense for B. Cool. For part C now, it's asking for what is the apparent weight of the car at the top of the hill at 30 meters per second. So apparent weight refers to what? What does apparent weight refer to? Yeah, I think both people said it at the same time. Yeah, normal forces, contact forces. So apparent weight is the sum of all contact forces, right? And in this case, the only contact force that we have here is normal force, right? So if we're trying to figure out normal force, if we're trying to figure out a force in general, this was an issue that came up with a lot of students in this past unit, is figuring out, like, what the heck do I do here? Like, what does this mean? Like, what do I do? What's the first step? Well, first of all, I have to know my definitions. I have to understand what's going on to a certain extent. Like, I've had to be at least somewhat paying attention to the lectures, understand, like, the terms and variables at least. So, like I said, we have to define what apparent weight is. Apparent weight is the sum of all contact forces. What's the contact force here? It's just normal force. Okay, so I'm looking for a normal force. Well, if I'm looking for a force, right, relative to some other forces that I've identified, like gravity, for example, that's what I drew for my free body diagram there. Well, if I'm trying to figure out one force, then in relation to another force, then most likely I'm going to have to set up a net force equation of some kind in order to relate two forces to each other, right? Well, there's force of gravity. We can get that because we have the mass, because we know mass times gravity is equal to force of gravity, so we can get that easily. And at the same time, we figured out what our centripetal acceleration is. We already know that there's a net force downwards because there's a centripetal force that is allowing us to traverse this circular path, right? Because there's a centripetal acceleration, there's a centripetal force, and there's a centripetal force that is giving us that centripetal acceleration there. We have a negative net force there because it's along the negative y-axis. So given this centripetal acceleration here, it's also easy for us to kind of relate normal force to gravity and then to overall net force, right? So once again, in order to figure out forces relative to each other, figure out what values of certain forces are, we're going to have to draw or write out a net force equation. So we have F net is equal to MAY, right? So this is in the y direction. And alternatively, we can even go ahead and just say MAC from the begin with, because we know that there's a negative overall net force here, right? That's due to the centripetal acceleration. So we can just say MAC right there, right? Because we know that the net force is dependent basically on centripetal acceleration in this case, because this is a circular path that we're traversing, right? So we say F net is equal to MAC, and then Fn minus mg, right? So you guys know that I like to draw include my directions right then and there with the equation. And if I'm going by that rule, then technically this should be a negative MAC to indicate a negative net force, right? The one thing that I'd have to keep in mind then to adjust this is that I can't just plug in this negative here, because then I get a positive net force. So when I'm including directions in my equation from the beginning, I have to make sure that I'm putting in like magnitudes of values. So for mg here, the g, I don't have to plug in negative 10, for example, if I'm calculating it. So it'd just be like minus 1500 times 10. And the negative sign is here indicated anyway. It's as if we pulled it out of the negative 10 meters per second squared and just brought it to the outside here. And that's the same idea here. So if our acceleration, centripetal acceleration is negative 7.5, well, it's as if I pulled that negative out, put it right here. And so I'm just doing negative times 1500 kilograms times the magnitude of that acceleration, which is 7.5 meters per second squared. Same deal, right? I could alternatively put MAC and just plug in the negative acceleration there from part B, but just kind of depends on how you want to set it up. I prefer to set it up with the directions included. Now, with this in mind, right, for my centripetal acceleration here, I have negative, this is 1500 times, what is it, 7.5? Yeah, 7.5 meters per second squared. And this is equal to the normal force that I'm trying to figure out, and this is minus 1500 kilograms times 10 meters per second squared for my gravity, right? And so all I have to do here, or is it 1500 or is it 1300? I'm so sorry. 1300 kilograms. So this is 1300, not 1500, sorry about that. So 1300 times 7.5 equals Fn minus 1300 times 10, right? And so at this point, we're just basically solving for Fn here. So we can kind of add this over here and then solve for Fn. For Fn, you should get around 3,250 newtons, I believe. But yeah. So if you want to figure out a specific force, you have to relate it to the other forces that we can figure out or calculate or whatever, right? So we wanted to figure out what the normal force was. We had information that allowed us to get gravity, and we have this information here that gives us centripetal acceleration. We know that there's a centripetal acceleration here pointing along the negative y-axis. If there is a centripetal acceleration, there has to be centripetal force, right? That is keeping us along that circular path. And so therefore, because there is a centripetal force, right, that centripetal force is necessary to keep us going along this path. If we are to continue along this path, there must be a centripetal force. And that centripetal force, right, has to be greater than the other forces along that axis in order to have some kind of centripetal force, centripetal acceleration, right? Because otherwise, if Fn is larger, right, then the F net is equal to MA. It's not equal to MAC anymore, right? Because AC denotes centripetal acceleration. It means that acceleration is pointing towards the middle. The acceleration vector is pointing towards the middle, keeping you along that circular path. So because there's a centripetal acceleration, because there is a circular pathway, there is a centripetal force. And that centripetal force has to be larger than the other forces along that same axis in order to keep you along that path. So therefore, the net force should be pointed along the same direction as the centripetal force here. So Fg has to be along the same direction as the centripetal force, or basically Fg is our centripetal force in this case, right? And so that just means that there has to be, this force here is overwhelming the other forces on the same axis. So Fg has to be bigger than Fn, so our net force has to be negative, or it's pointed along the negative y-axis. And so we just have to relate whatever force we're looking for to the other forces to help figure out what's going on. That's the idea of how to figure out, like, when do you set up all this junk here, right? When do you set up a net force equation and all that? So hopefully that made sense for C. But if everything's okay for C, then part D is asking us what is the fastest the car could go without leaving the ground as it goes over the hill. So this is a classic question here. It's going to pop up on a lot of exams, a lot of quizzes, or well, on your exam and on your quizzes, and homework and all that. It's very, very common for them to ask you basically what is the fastest or what's the maximum speed, right, that the car could go without leaving the ground, or without, like if it was a loop-de-loop, right, if it without losing contact or barely losing contact with the rails or something, or the track. So in that case, you're absolutely right. Fn is equal to 0, right? So it's a speed, the maximum speed that we can go or travel with, that we're just barely keeping in contact with the ground, right? And so in that case, Fn would actually have to be 0, right? So normal force has to be 0. It's the point where it's like, okay, if I went a single meter per second over, this car is going to be flying, right? Or if it's on a loop-de-loop, right? If I go, well, it wouldn't be faster, right? Because if you're at the top here, you have to go really fast in order to make sure that you're still along the track. But in this case, if you're at the top, it'd be like, what is the minimum speed that would keep you in contact with the rails in that case? Because otherwise, if you go pretty slow, then you're just going to fall down, right? So that being said, we're just looking for the fastest speed that the car could go with a normal force equal to 0, which is just when there's no longer any contact with the ground. So just barely leaving the ground. So in that case, we're going to set up another FNet equation, right? And the reason why is that since we have this idea here, normal force is equal to 0, right? We have some other forces like gravity, and we can figure out what centripetal or our net force is, right? Then, in this case, we can kind of look at, well, okay, what concept or what value indicates or incorporates speed with the force values that I already know. So this is the idea of how to solve like any problem, basically. It's like looking at what values I have, what values I'm looking for, and how they kind of relate. So if I have a normal force here that I know, and I have gravity or whatever, and I calculated centripetal acceleration, well, how am I supposed to relate forces to speed? How do you guys think we're going to relate forces to speed? So yeah, you're close. You're on the right track. You're very close. It wouldn't be MAY though. It would be something else because remember we have to include or factor in the speed, right? So yes, we have to set an FNet equation, absolutely right, and then we can use the centripetal acceleration, right? So remember here where we said negative MAC is equal to Fn minus mg. Well, this AC, we already determined that to be v squared over r. So you're very close in the fact that you set up that equation, right? So it's Fnet, and instead of being equal to MAY, it's, add this negative sign here on the outside, so negative mv squared over r, because that's just equal to AC, right? And then that'll be equal to Fn minus mg. Or, yeah, Fg, mg, same diff, right? So in that case, you're just going to be looking for what the v is here, right? So we know that this is 0, right? Because we said it's when the car or the object just barely loses contact with the surface. So in that case, negative mv squared over r is equal to negative mg, right? Negatives cancel out, mass cancels out. So we're left with v squared over r is equal to g. V is equal to root rg. And so we know that our radius was 120 meters, and gravity is 10 meters per second squared, right? So you should get a, yeah, go ahead. I don't know if it has a specific name, but it's very, very common because it's a situation in which you have that normal force being equal to 0 usually. I'm not sure if it has a name. I can't remember if it does, but I'd have to go look back at the lecture if it does have a name. But yeah, this is very common. V equals root RG. Mm-hmm. Yeah, you'll get this like specific form very, very frequently on your quiz and homework and exam and stuff like that. But this is a really, really important situation that you have to watch out for. You have to really be able to solve these types of problems where they're asking you how fast or how slow the car would go and still keep in contact with the hill or whatever, or the track, or, you know. So I'd really know how to solve these types of problems here. But for V, you should get around like 34.64 meters per second, I believe. Sound good for problem 2 there? Okay, so we're moving on to problem 3, I think. Yeah, problem 3. And heads up as well, problem 4 here is different than the problem 4 that I had, so I'll upload my written homework as well to Google Drive, so you have an extra practice problem that you guys can do. But yeah, problem 3, motorcyclist revisited. In the group problems, you consider the forces acting on a motorcyclist driving in a vertical loop at constant speed at the top and bottom of the loop. In this problem, you'll consider what happens at another point of the loop, point A, which is the rightmost part of the loop. The radius of the loop is 2.5 meters. Combined mass plus rider is 250 kilograms. Speed is 10.5 meters per second. Cool. So for part A, they want us to draw a free body diagram for point A. And it says, hint, the normal force is perpendicular to the loop. Weight force is down. Motorcyclist is driving at constant speed, so there must be a third force acting on them. What is it? Okay, so they already kind of gave us what's going on here for the most part. They told us that normal force is pointing to the left, right? And that makes sense because if we imagine this bike kind of here, right, there's a weight to this bike, and that's going to be this way. So if like you flip your paper kind of horizontally, right, you can see that if this was the surface, right, if this was the floor, then normal force would be pointing perpendicular to it, right? So normal force points to the left in that case, right, because it's as if the track is kind of pushing up and against the bike. And then obviously we have gravity pointing downwards. That always points downwards. So if, right, we have this circular pathway, well, knowing the idea, the concept of centripetal force, centripetal acceleration, in order to continue moving along a circular path, we have to have a centripetal force, right? And we have to have a centripetal acceleration. So there must be a force pointing towards the, towards the center of the circle, or radially inward, right? That would be the net force in this case, right? That would help us continue moving in that circular path. So theoretically, this force should be normal force, right? Normal force is pointing directly towards the center of the circle, radially inward, and that should be the net force on your object. That is keeping it moving in that circular motion, right? Now, based on what you see here, well, there's a force in the x direction. There's also a force in the y direction. So things aren't quite all dependent on normal force, right? Because technically, it's like having a net x force and a net y force. So in order to just keep normal force as our centripetal force, as the force that is the only force basically that is keeping us kind of in that circular motion, the only force that kind of factors into or directly kind of influences our circular motion or circular pathway here, then we have to cancel out the force of Fg, right? Because Fg has to be canceled out by something else to where F net y is equal to 0, and you only have an F net x. And in that case, F net x will just be equal to normal force, and that's equal to MAC, right? Because in this case, normal force is offering our centripetal acceleration, pointing radially inward here, keeping us in that circular motion. So gravity has to be canceled out by something else, by some other force, right? In order to have net force here be 0 on the y-axis, and then the only force keeping us in the centripetal motion, or the circular motion, be the normal force. So what force do you think is going to be acting against gravity here to keep things kind of dependent on the normal force here? to keep the normal force as the only force basically kind of in play or factoring into centripetal force and centripetal acceleration. Yes, it is friction. Now, the important question here is what kind of friction? I heard two statics, I think, maybe one kinetic, I'm not sure, but it is static. And the reason is because, remember, kinetic is when you have objects sliding against one another. Objects are in motion, sliding against one another, right? Now, if you think of a bicycle, right, is the bicycle ever sliding really? It's not sliding, it's kind of gripping onto the road. And that's why you have that kind of that traction on the tires, right, or on the wheels, right? Because they're kind of gripping along the pavement, along the road, to help you kind of almost, it's as if the bike is, or the tires or the wheels are kind of crawling along with every kind of gap in the traction, right? So it's kind of gripping along the pavement, along the road. And so in that case, static friction force, remember from the previous units, right? We could think of static friction force as kind of two ways, right? And I mentioned that multiple times. And those two ways are basically static friction force is the force that is keeping an object from slipping, right? And it's also kind of a grippy force that keeps or allows objects to kind of propel forward, grip together with the ground, right? And kind of allow for that motion. So if I'm walking, on the side of the street or on the sidewalk or whatever, right, there's traction on my shoes. So as I move forward, right, static friction force is actually the force that allows me to be propelled forward, grip together with the ground, and move in the direction that I want to. So in this case with a bicycle, those wheels, right, or those tires or whatever, if you have a car, for example, are going to be propelled forward or allowed to move forward this way via static friction. So if I am at this location here and I want to continue moving upwards, static friction force has to point upwards in order to keep me or allow me to propel upwards in this direction. Kinetic friction force, just think of kinetic friction force as literally just solely sliding. Like, think of smooth surfaces on smooth surfaces. So like a block on ice, right? A sled, right, on ice, for example. Or if you yourself go sliding on ice. So it's just like two flat surfaces basically sliding against one another. That's the idea with kinetic. Static friction is more like, especially when it concerns like an object moving, it's going to be when there's a grip to the object, basically, or grip to the surface. And that grip is what allows the object to kind of move. And so that's why we see static friction instead of kinetic. Think kinetic as sliding. You really wouldn't want, and exactly, a block getting pushed and moving. That would be kinetic, right? Now, static friction is kind of grippy, right? So in order for the bicycle to keep on moving in the y direction here, it kind of has to grip with the track, with the path. Rolling friction is present with any wheel. Like any wheel type surface, rolling friction is present. The issue with rolling friction is that it's almost always negligible. Like there's very few problems or very few circumstances where you have to actually factor in rolling friction. It's present, but it's smaller and more negligible than other friction forces. So that's why I said at the beginning of the semester, like kinetic and static are the ones that you have to worry about. Rolling friction is very rare. I think there was one problem on a quiz for this section where they asked us to factor in rolling friction, or they basically just told us to factor in all friction forces that are possible. And so rolling friction is possible if you have a wheel, but it's so small and negligible that we just kind of ignore it most times. And in a problem, they'll pretty much either tell you to ignore it or it's pretty much natural to ignore it anyway. Otherwise, they might say like, oh, include for all forces, regardless of their size. If they say regardless of their size, well, then you have to include maybe, rolling friction in if you have a wheel, right? Because yes, it's small, but it's present. Otherwise, if they're just telling you to write a free body diagram or whatever, right? Then you just factor in the forces that are most significant, right? So if a problem says there's a rough surface, it just depends, right? Rough surface, like I said, smooth surface on smooth surface. Like if a block is sliding on a rough surface, well, the block is smooth, right? At least, like I think of it as the block is a block, right? So this surface here is just like the bottom of the block is kind of flat, right? As opposed to a wheel or a tire, for example, you have like little gaps, right? I even know what they're called, like just like traction, right? Along the tire to kind of grip with the road. Same with your shoes, right? Your shoes, like if you look at the sole of your shoes, you might have like little, I don't know, dots or something, right, on the bottom of the shoe to kind of help you grip with the ground. So really static friction is two scenarios. Either the object is like, or like if an object is trying not to slip, right, then there's static friction. And they'll say like, they're almost always going to say like slip or about to fall or something like that. Or you alternatively have a situation where like you have this one here where your object is trying to grip with a surface. And so if you have like a wheel or something like that, or a tire, or especially in these circumstances with cars and stuff like that, those objects are going to be gripping with the surface. And so in that case, the friction that you would have is static friction. And we, like I said, I apply static friction here because it's the force that is going to help propel me in the direction that's going to help me grip with the surface, move in the direction that I want to against the force of gravity, in order for this to be canceled out in the y direction, and in order for the normal force here to be the only force that is factored in when we're talking about net forces, when we're talking about centripetal forces. Make sense? Yep, okay. Now they're asking us to determine the magnitude of all three forces on our free body diagram for point A. So we're trying to figure out Fs, Fn, Fg, right? So for normal force, we know that that is going to be the only force that is going to be factoring into our centripetal force, right? So F net is equal to MAC is equal to mv squared over r is equal to normal force, right? Well, mv squared over r, we have the mass from earlier, which is 250 kilograms, times the speed, right? That was 10.5 meters per second. Square that, and then divide by the radius of curvature, which was 2.5 meters. And that gives us our normal force. And that should be around 11,025 newtons, my bad. For normal force. Now for gravity, right, that's simple. Gravity is just equal to mg. So that's 250 times 10, and that's 2,500 newtons, right? And for static friction, that's also pretty simple, right? Because we already said that these forces have to cancel out in order for normal force to be the only force basically in question here to offer centripetal acceleration, centripetal force, right? So in that case, we know that Fs prime minus Fg should equal 0, right? Because they should cancel out. So Fs prime is equal to Fg. So Fs prime is also 2,500 newtons. So in this problem, we were concerned with kind of canceling out the other forces that aren't relevant to the direction or the axis that is going to be providing a centripetal force and centripetal acceleration. So in problem 2, for example, right, let's say if we had some other force this way, like we had friction, right, if we had static friction this way, for example, right? So static friction is along the x-axis. We don't care about the x-axis really, right? And so it makes sense that there has to be a net force here, because that's going to offer us centripetal force, centripetal acceleration, that is going to keep us moving in that circular path. Now, we might also have some static friction force along the x-axis, but what we're concerned with is looking at these forces, that force that's going to be pointing towards the middle, basically. And so if we want to focus on that force in the middle here, right, and we want to make sure that we're traveling properly along this circular path, well, if I go here, 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 right, if gravity overwhelms me, then I'll just fall back down. So I have to have some force that is going to allow me to propel forward, propel upwards, right? Cancel out the effect of gravity. And then the only thing that is going to really play a constant factor in allowing me to traverse that circular path is normal force here, which is pointing towards the center of the circle, centripetal acceleration, centripetal force. But yeah, makes sense for problem 3? Okay. So if everyone else is okay as well, problem 4 then, we can move on to that. Yeah, about 5 minutes left from my scheduled time, but that's fine. We can go over and then we can move on to the online homework. So problem 4 is saying in the online homework this week, we look at passengers in a carnival ride moving at constant speed in a circle. As they spin, they feel their backs pressing against the wall, holding them in the ride. So for part A, we have to draw a free body diagram of the passenger when she's at the rightmost spot in the circle, right? So what forces do we have acting on the passenger in this case? So we have gravity, right? And we have normal force, right? So normal force in this case, right, because the surface is kind of up and down here, right? Normal force we said is going to be perpendicular to the surface of contact. So normal force is pointing like this, radially inward, right? So this is normal force. And then what other force do we have acting on the cyclist here? Or I said cyclist, the person. I was thinking about the last problem. Yeah, static friction, right? So we should have static friction there. And naturally, right, since the person's kind of not moving, right, they're not slipping in this case, then static friction force should be equal to the gravity in order for there not to be any net force in the y direction, right? So we want to make sure that centripetal force here, which is the normal force, is the one that's in play, basically, or in question, that is going to give us that that circular motion. And so that's part A. For part B, it's saying for the ride spinning at some unknown speed, the normal force on the passenger is 800 newtons and the weight of the passenger is 550 newtons. Coefficient of friction between the passenger and the walls of the carnival ride is 0.8. At this speed, the passenger is not slipping. What is the magnitude of the friction force on the passenger? Now, this is very tricky because they gave you static or coefficient of friction here. How do we figure out friction force? So that's why I said it was tricky, because that's what you would normally think, right? You would normally think that, oh, static friction force is equal to mu times Fn. This is only ever true if static friction force is at its maximum, right? And static friction force is at its maximum when the object is about to slip. They indicated here that the passenger is not slipping. There's no risk. There's no danger for the passenger to slip. So pretty much at every other interval, right, if you remember the definition of static friction, it's actually less than or equal to mu Fn. It's equal to mu Fn when it's at its maximum, when the object's about to slip. Otherwise, it's less than mu Fn at every point. Now, if it's less than and it's not slipping and it's not at its maximum, well, how do we figure it out, right? So we want to figure out what static friction force is. Once again, if I want to figure out a force relative to other forces that I can calculate or figure out, or the information given to me, then I want to set up a net force equation, right? So I have here normal force is 800 newtons, right? And the weight of the passenger is 500 newtons. So if I'm concerned with a force along the y direction, I should also be concerned with another force in the y direction. So for F net y, right, I know that's 0 because everything should cancel out in the y direction here. The person isn't moving along the y direction. They're only moving in a circular direction, and so since there's moving in a circular direction, there's still motion, and that motion is offered by centripetal acceleration. centripetal force, and that's by normal force, right? And so that way all the other forces have to cancel out. So Fs minus Fg, and that's equal to 0, so Fs prime is equal to Fg, and so Fs prime is just equal to the weight, and that's 550 newtons. Sound good for part B? Does that make sense? Cool. Part C is asking for the speed of the carnival ride. They say the speed of the carnival ride suddenly drops by a factor of 1.5. In this case, what is the magnitude of the normal force? So, if I'm looking for speed, right? Or they said speed was decreased by a factor of 0.5. That just means that the speed was divided by a factor of 1.5. Basically, that's what it means. So speed was divided by 1.5, right? Now they're asking what the normal force is in this case. So once again, if I'm looking for a normal force, if I'm looking for a force in general, I'm going to be relating that force in question to other forces that I can figure out or that are given to me. So I have to set up a net force equation, right? So in this case, I know that this normal force is equal to my net force in the x direction, which is equal to my centripetal force, basically, right? mv squared over r. And so if you think about it, right, well, I had this normal force of 800 newtons from before. Now, this normal force is going to change. We want to figure it out because we have this decrease in the speed, right? If this decreases, then the overall net force decreases, and so the normal force decreases, right? And so all we have to figure out here then is to basically relate our original speed, right, whatever that was, and then to our new speed and figure things out that way. So in this case, let me actually write this as, instead of mv squared over r, we'll write mac first, right? So I know that Fn is equal to 800 newtons initially, right? And that's equal to mass times the centripetal acceleration, right? So I know that the weight here was 550 newtons, and that means 55 kilograms was the mass, right? Because weight is mg, so if g is 10 meters per second squared, I can just do 550 divided by 10 to get my mass, which is m. So this should equal 55 kilograms, because this is MAC, right? So 55 kilograms times AC, right? And then that gives us centripetal acceleration of around 14.54 meters per second squared, right? So in that case, we have this centripetal acceleration. Now, we already said that the centripetal acceleration is going to decrease. And the reason why is that we said that earlier centripetal acceleration is equal to v squared over r. Well, if v is divided by 1.5, right, then this number is going to change. And so if we say v divided by 1.5, right, whatever that value is, and we square it and divide by r, that would give us our new centripetal acceleration, right? This is new centripetal acceleration. Well, if I calculate this out, I can see that this new centripetal acceleration, if I simplify this part right here, I can see that it's equal to v squared over 2.25 r, right? If I simplify it out, that's what I get. Because this will be v squared over 2.25 divided by r, and then this will just get multiplied over here, right? Because this is just like saying v squared over 2.25 times 1 over r. This is the same thing. And so you get v squared divided by 2.25 r. And then you can see here that really what this is just taking v squared over r, which was your original, right, and multiplying it by a factor of 1 divided by 2.25, or dividing it by a factor of 2.25. So if your speed decreases by a factor of 1.5, your acceleration decreases by a factor of 2.25. So once we have that centripetal acceleration figured out from earlier, that 14.54, we can divide it by 2.25, right? Because in that case, we'll get, what? For our new centripetal acceleration, it should be around 6.46, I think, meters per second squared, right? So that's our new centripetal acceleration. So with that new centripetal acceleration, we can multiply it by our mass here to find out our new normal force. So Fn is equal to the 55 kilograms that we figured out earlier times this new centripetal acceleration, which is 6.46, and that should give us a normal force of like 355.4, I think. Does that make sense? Are you guys following along? So I don't have, like I said, this is a different problem than what I had. And so I just want to make sure that everything is adding up and you guys are following along and it makes sense to you. Because if you see something out of the blue or out of the ordinary, let me know, because I don't have an answer key for this. I don't know what's right or wrong. I'm just basing this on my knowledge of physics, which I hope is sufficient enough to help me solve a problem like this. But yeah, hopefully that makes sense. Yeah, I mean, they wanted you to decrease the speed, and so logically, if you decrease speed, you're going to decrease your centripetal acceleration. Well, if I decrease centripetal acceleration, I have to think about, well, what's offering that centripetal acceleration to begin with? That's going to be the normal force, because it's pointing towards the center of the circle, right? And so if velocity or the speed drops by a factor of 1.5, your acceleration would drop, right? And if the acceleration drops, then the normal force has to decrease. Well, I know that the normal force is equal to my centripetal, it is my centripetal force, right? And so that's m times ac. Well, I don't know how much my acceleration decreased by. I know that my speed decreased by a factor of 1.5. Well, how does decreasing the speed by 1.5 affect my acceleration, my centripetal acceleration? So that's the idea that I have to figure out. I have to figure out how large was the change in my centripetal acceleration, which is what we figured out here, that it decreases by a factor of 2.25. And once I figure out how much it changes by, I can figure out the new centripetal acceleration and then use that to figure out the new normal force. Because otherwise, if this was, remember we solved for the centripetal acceleration earlier, it was 14.54, then normal force would actually be a lot greater. So if you decrease speed, you're decreasing that centripetal acceleration and therefore decreasing the centripetal force and affecting the value of normal force. So we have to figure out how much this speed decreasing is going to cause a decrease in acceleration. So like we have to figure out how much that change in velocity or change in speed is going to change the acceleration. And then from that change in acceleration, whatever new value that we get is the value that we multiply by our mass to figure out our new normal force. Does that make sense a little bit more? Yeah, I mean, I guess it kind of depends on your professor too. Some, like obviously, I think it's just a crunch for time, so maybe they just might go through things a little bit more quicker. They might not go as in depth as I do or explain like all these little nitpicky details, but if you're having trouble with what the professor is saying during lecture, I highly recommend, if you at least if you have Dr. De Jong, he has videos uploaded on the Blackboard, right? If you watch those videos, those are the videos that I watched because it was during the pandemic, and so those videos are pretty much what helped me understand all the physics that I know. So I find them much more, I guess, based on other students' experiences too, like what they tell me that they know and what they don't know. I felt like so far those videos are more detailed and more helpful than maybe any lecture. And so if you watch them, and they have like little like practice questions in between, questions for clarification to help you make sure that you're understanding as you go along. And so I'd watch those if you're not really benefiting from the live lectures. And obviously if you don't have Dr. De Jong, then I'm going to try my best to record my own type of lectures that will go into detail and hopefully will be still detailed but shorter than the total amount of time that you spend in lecture. So instead of going to 3 1-hour lectures a week, I'll try to make like, I don't know, an hour video or something, or 45-minute video or whatever it is, to try and give you a more concise but still detailed explanation of what's going on. But yeah, hopefully that makes sense, Jonathan, as well for part C. Like that cleared it up. Hopefully that kind of makes more sense now. But yeah, that's part C. Part D now is asking you, well, is the friction force at this lower speed and at that lower acceleration sufficient to keep the passenger in place, or will she start to slip? So what this means is just we're going to compare the magnitude of the maximum static friction force to the weight of the passenger, right? So in this case, we want to figure out what the maximum static friction force is. And that's why they gave us the coefficient of friction earlier. So we know this is equal to mu Fn. This is 0.8, and times our new normal force, that's 355.4, right? And so that's around 284.34 newtons, right? That's our maximum static friction force. So it's basically asking you, okay, does this maximum static friction force, right, allow you or allows the passenger to keep in place, or will she start to slip? Because the weight of the passenger is Fg, and that's equal to 550 newtons. That was given to us before, right? So the reason why they want us to compare maximum static friction force to the gravity in this case is we're assuming that at this lower speed, right, we're observing what's going on this lower speed. So at this lower speed, let's say we want to see if they're going to slip or not. So this lower speed gives us a lower normal force. And so if we can calculate what the static friction force is at that lower normal force, right, then we can say, okay, this is the force that static friction is going to apply to prevent slippage. Is that force enough to overcome gravity or not? In this case, we can see it's not, right? So 284.34 is way less than 550. And so gravity is going to overwhelm the static friction force. It'll be a lot smaller, right? And so that person is going to slip at that lower speed. Now, if we increase things, if we sped the the carnival ride up, right? If we made it go a lot faster, we're going to have a greater centripetal acceleration. Greater centripetal acceleration means greater net force, greater centripetal force, greater normal force in this case. If normal force is greater, then our maximum static friction force is greater. So this might be like, if we increase it to a point where it's like 600 newtons, right? Then at that faster speed, static friction force would be applying, or would apply, 600 newtons of maximum static friction force, right? Is that enough to keep the object from slipping? Is it enough to overwhelm or overcome the force of gravity? In that case, 600 is greater than 500. Yes, it overwhelms it, right? And to a certain extent, like, you'd actually kind of be moving a little bit upwards too, right? So since it's less, you start to slip because going at that lower speed gives you a lower normal force. That lower normal force gives you a lower maximum static friction force. If the maximum static friction force is lower, right, then your gravity, for example, or whatever other force is going to be opposing it, then it's going to slip. Does that make sense for part D? Yep, go ahead. So, yeah. So in that case, like, they're not slipping, right? And the weird thing about static friction force is that, like, I mean, it's the force here that is keeping the person static, still not slipping, right? And so that's where the definition kind of gets a little bit iffy. I wouldn't say necessarily that the person would then kind of be like moving upwards in a sense, because it would make sense that, okay, if the net force is positive, right, because then in that case static friction force is greater than Fg. If this is larger than Fg, it would make sense that it would be moving upwards, right? But I think in a sense that static friction force is a force that prevents slippage. Well, if the forces are less than the amount that it takes for it to slip, then okay, like, we're not slipping, and that's the end of it, right? Like, we're not going to say that, static friction force is allowing you to, like, move or something, right? Because if I think of a car, right, parked on a hill or something, then there's a maximum static friction force to that, and maybe gravity is going to pull it downwards, right? Well, if the gravity is less than the maximum static friction force, the object is, or the car is still, it still has its brakes on and it's not moving. But maybe static friction force is greater than, gravity, and so overwhelms gravity. Does it mean that the object is going to be moving? No. But it just means that it's not slipping. That's all. Yep. But yeah, that's a really good question. So I wouldn't go as far as to say that, if static friction force is then greater than gravity, then there's a positive net force, and so the person is moving upwards or something like that. It just means that they're not like slipping, basically. So that's it. Otherwise, like if you had maybe the idea where static friction force is the force that kind of propels you forward, right? If you're walking or with that bicycle, for example, right? Then maybe if static friction force is, for example, in this here, right? If it's less than gravity, then okay, then that person is gonna fall downwards because it's not enough force to allow them to kind of continue gripping with the road or with that circular path and move upwards. So I'd say maybe if the context was that there's some kind of, it's weird because, like I said, static friction force is like grip or preventing slip. That's how I think about it. Grip or preventing slip. If it's preventing slip, if it's greater than whatever forces are acting against it, then fine. Like there's no net force necessarily, but, or at least we don't say that the object is moving in a certain direction or another. We just say that it's not slipping. Cool. If it has that grip context, like tires on a road or bicycle moving in this direction, right, trying to move in a certain direction, then okay, sure. If that force that is allowing the object to propel forward, to have a certain motion, right, static friction force in this case is kind of as if it was our F pedaling force, right, or F push force or whatever. It's that force that is allowing us to propel forward. So naturally, in that case, if it is the force that is allowing us to propel forward, if it's not greater than or it's not overcoming or whatever the other forces in its same direction, then you're going to have some motion. So in this case, like if static friction force doesn't equal Fg offering no net force, right, then gravity will overwhelm it and bring the bicycle down, right? And the idea here, why it's the same, is that we don't necessarily want a net force moving, or a net force in the y direction, right? Because we don't want to just be like moving and then move like this, right? We want to make sure that we're moving this way and maintaining that circular motion. Normal force helps us maintain that circular motion. We want to make sure that static friction isn't too small, right? It's not too small that we're falling down, and it's not too big to the point that we go like this and just move upwards, right? We want to make sure that it's a healthy balance, that it's allowing us to propel forward to make that really tough incline against gravity, and then just be enough where it cancels out gravity, and then the only force that is allowing us to move in that centripetal or circular motion is normal force. Hopefully that kind of clears things up as to the two situations, like slip versus grip. Make sense? Okay. So that's our written homework. Really sped through that this time. And the reason why is that I want to make sure that there's enough time for like more conceptual questions, stuff from the online homework and all that. Because from what I heard, really the exam it seemed like they pulled a lot of more unique problems, like that elevator with the two boxes, which, I mean, I don't want to sound biased, but basically, like, in that case, and I'm trying to be as sensitive as possible, but moving forward, what they're going to do in any of these exams or quizzes is they're going to pull stuff like that, right? And you have to be prepared for it, in the sense that you can't just kind of memorize how problems are solved or types of problems are solved. You have to understand why they're solved that way. Sure, you can understand, like, oh, a two-box problem is solved like this, right? Or this is how you draw a free body diagram for a two-box problem, or, for the elevator problem, right? It's solved like this. Sure, you can memorize or understand or figure out that yes, in this situation or this context or this scenario, this type of problem requires this step, or in order to figure out this force or this question, we have to do this, this, and that. But you have to understand why as well you're doing that, right? And you have to understand what those scenarios mean. What do they, mean for the overall context that we're looking at? And so if that, idea of the elevator question from the exam, right, that came up a lot of times before, but it was just a person in an elevator or a scale in an elevator or whatever, right? It was just one simple object. But you have to understand what the elevator is doing. It's not a unique, very complex scenario. All it's doing is telling you that, okay, if I'm on a stable surface without any net force, no acceleration, nothing is pulling me up or pulling me down, right? Then I'm going to have, for example, like if I've stepped on the scale or something like that, right? Then I have a normal force, I have a gravity, right? When I step on an elevator, the elevator is pulling me up or pulling me down. And so in that case, your forces in the y direction no longer cancel out. One of them has to be bigger than the other to offer a net force to pull you upwards or pull you downwards. That's the concept, right? Now, we might have understood how to solve it, what are the steps to do it, but the issue there was understanding, like, why the heck are they asking us about an elevator? What does the elevator mean, right? And the idea is that it just means that, okay, well, if I have an elevator, it just means that there's a net force. And so just understanding more conceptual side of physics, understanding why these problems are solved the way they are and not just how they're solved, is what I'll try to target in the next few weeks. So with that being said, I'll move on to the online. Since this is the first time to kind of go over the online, I'll just leave it up to you guys. Do you guys want to go through as many problems as we can individually, or are there specific ones that you want to pull out and go over? Yeah, I mean, oh, sorry, go ahead. I was asking or answering or just commenting on Rachel's comment there in the chat. But yeah, go ahead. No, go ahead. It's fine. I kind of already just addressed the 2-box thing. That's fine. This one? Okay. Okay. Yep. So for this one, problem 2, a lab technician is centrifuging a blood sample at a rotation rate of 3 times 10 to the third revolutions per minute, right? The radius of the circular path followed by the sample is 0.15 meters. So I think a lot of mistakes that people make initially when they're looking at revolutions per minute and stuff, they think like, okay, revolutions per minute, that's something per minute, like a distance per minute or, something like that. So basically, what a lot of people make a mistake on is that they consider this, okay, like, oh, that just means like that's the speed, right? So the speed is 3 times 10 to the third revolutions per minute. That's incorrect. When you see revolutions per minute, cycles per second, cycles per minute, revolutions per second, that's an indication of not speed, but frequency, right? So whenever I see rev per minute, rev per second, what was that? Rev per second, cycle per minute, whatever, right? That's going to be my frequency, right? How many revolutions I can get or how many cycles I can get per minute or per time interval or whatever, right? So when they ask determine the linear speed, well, I know linear speed is v, right? And I have frequency and I have radius, right? Well, based on the equation that we know from the lectures and stuff, we know that v is equal to 2 pi r times frequency. So 2 pi times our radius, which was 0.15 meters, right? And then we have revolutions per minute, right? So for revolutions per minute here, we want to have the answer in meters per second, right? So we want to change this minutes to seconds. So we can say like 3 times 10 to the third, right? Revolutions per minute, and then that minute divided by 60 seconds there. So a minute cancels with minute, divided by 60 seconds. And so our linear speed in this case should be around 47.12 meters per second. So 2 pi r, right? That's our circumference, by the way. 2 pi r is our circumference, which is the total distance around the circle, around the perimeter of the circle. And so we want to check then the linear speed, right? So I kind of think about speed as like at any or at some point in the circle, right? I'm traveling at 47 meters per second or something, right? But let's say that I travel completely around the circle, right? I take 3 times 10 to the third revolutions per minute. So I travel every minute 3 times 10 to the third revolutions, right? So that just means like in every minute I travel around the circle 3,000 times. That's what it means. So I can think about that as a frequency. How frequently am I traveling around the circle? That's the idea here. How frequently am I traveling around the circle? Oh, I travel around it 3,000 times per minute, right? And the reason why I want it in seconds is that since we want meters per second, we want to make sure that we're given our answers in meters per second. So this just tells me the individual object, right, itself is moving at 47 meters per second, but I might be traveling, right, 3,000 revolutions. I travel around the circle 3,000 times per minute. So that's when you see revolutions per minute, cycles per minute, revolutions per second, cycles per second, that's going to be an indication of frequency, not speed. Now for part B, magnitude of the centripetal acceleration, right? We know that centripetal acceleration is equal to v squared over r. So we just take our speed from before, square it, and divide by the radius, which is 0.15. That should give us around 14,804.4 meters per second squared, I think. Yeah. And then part C, I think, yeah, part C is the last part of problem 2 here. So consider a blood cell in motion in the middle of the sample with a higher density than the fluid around it. What force is responsible for providing the centripetal acceleration on a blood cell? So in this case, if you think about this thing in a centrifuge, right, and you have your little microcentrifuge tube, right, you have this liquid in here. Well, the liquid has a buoyancy force of buoyancy, right? And since the sample has a higher density, right, it's a higher density than the fluid, then it's going to be sinking, right? So if its intended motion is sinking downwards, there's a drag force in the opposite direction, sort of like our friction, basically, that's going to prevent it from moving downwards, basically. So it has to point upwards. In this case, F drag has to point upwards as well. And so you can see here that since buoyancy and drag point towards the center of the circle, point towards the center of the centrifuge, right, then drag force and buoyancy, that's B and C, right, those are the forces that are going to give you centripetal acceleration because they're pointed towards the center of the circle. Does that make sense? Okay. Someone asked for problem 9 as well. Let me jump to problem 9 real quick. So problem 9, this one is a little bit longer. Is there a specific part you want to go over? Or do you want to just go over like the whole thing? That's fine. Like either way, it doesn't matter to me. It's just I want to make sure that we're going over as many problems as possible. That's all. So I mean, is everyone having a problem with problem 9 as well? Okay. All right, we can go over problem 9. Problem 9, at its Ames Research Center, NASA uses a large 20G centrifuge to test the effects of large accelerations. Okay, 8.84 meter long arm here rotates about one end to horizontal plane. Suppose that he's aligned along the centrifuge's arm with his head at the outermost end. Maximum sustained acceleration is 12.5 g. So 12.5 times the acceleration of gravity, right? So part A is asking us how fast must the astronaut's head be moving to experience this maximum acceleration. So for the maximum acceleration, we saw that the maximum acceleration is 12.5 g, right? Now, when we refer to the maximum acceleration here of like this arm kind of moving in a circular motion, right? That acceleration is going to be our centripetal acceleration in this case. So centripetal acceleration is equal to the 12.5 g, right? Now, if we're asking for how fast in meters per second must his head be moving to experience the acceleration, then we're looking for speed, right? So we know that centripetal acceleration is equal to v squared over r, right? So in this case, we're just solving for v here, right? And we have our r because from the pivot, from the arm itself, all the way to his head, it's 8.84 meters, right? So it would be 12.5 times 10 meters per second squared times 8.84 meters, right? We multiply the r over, and then take the square root to get v. And so then you should come up with around 33.2 meters per second, right? Now, B is asking us for how fast in RPMs, revolutions per minute. What is that an indication of? Frequency, right? So how fast is the arm of the device turning to produce the maximum sustained acceleration? So we're looking for the frequency in this case. Now, we know that we have this, our speed from before was the 33.2 meters per second, right? And so this is equal to 2 pi r times frequency, right? So we're just looking for the frequency in this case. So for our speed, 2 pi r, so we have 2 pi times our radius, right? And this is still to his head, right? 8.84 meters times the frequency, and that's equal to the 33.2 meters per second, right? And so then that gives us frequency of what? Let me calculate that real quick. It's like 0.6, right? And that's going to be I think revolutions per second, I believe. Yeah, revolutions per second. And so let me see here actually real quick. Yeah, no, that's right. That's right. Yeah. Yes, 0.6 revolutions per second. And so we want it revolutions per minute. So 60 seconds, that's 1 minute. Seconds cancel out with seconds. So then we get, this should be 36 revolutions per minute roughly. So that's our revolutions per minute, that's our frequency. Now for C, it's asking how fast are the astronaut's feet moving if he's 2 meters tall and the arm is rotating with a speed found in B. Well, if we're then looking at the speed with B here, and when they say speed found in B, it really should be the frequency found in B. That's what they mean, the 36 revolutions per minute or the 0.6 revolutions per second here. So what they're actually asking for here, when they indicate the units here, they're asking for the linear speed of the astronaut's feet. Well, we found linear speed of his head, which was from the arm to his head. Now in order to find his feet, it has to be from the arm to his feet. Well, if he's 2 meters tall, then from the arm to his feet is 6.84 meters, right? So in that case, we can kind of set up the same thing here. We can say that v is equal to 2 pi times 6.84 meters, right? That's the radius from the arm to his feet. And then that's multiplied by our frequency from before, which is 0.6 revolutions per second. And that should give us our linear speed. And let me calculate that as well. 6.84 times 0.6, right? And that should give us, yeah, somewhere around 25.79 meters per second. So they're asking for how fast he's moving. In meters per second, that's linear speed. Meters per second is linear speed. And then when they're saying speed found in B, they're just referring to the frequency, right? Revolutions per second or revolutions per minute or whatever. And the reason why we use revolutions per second here is that we have meters, we have seconds, we want meters per second. So if we have minutes, we have to convert them seconds. And so you're just using his radius here, right? They said he was 2 meters tall. And if we're trying to figure out how fast his feet are going, so we're just concerned about this part right here. from the arm pivot to his feet. And so he's 2 meters tall. This whole thing is 8.84, right? Then this little section here is 6.84, because 6.84 plus 2, that's 8.84, right? And so that's why we use 6.84 meters here. And we're, like I said, we're trying to figure out linear speed, and we have our frequency from before. Now for part D, what is the difference between the centripetal acceleration of his head and feet? Then in this case, you're just looking for same deal here, right? For centripetal acceleration, we're going to be using some of the same values, right? So we had centripetal acceleration for his head earlier, right? And that was 12.5 g, right? That was the 125 meters per second squared, basically, right? And so AC head, we want to subtract that from AC feet, right? So if this was 12.5 g, which is 125 meters per second squared, right? AC feet is just equal to v squared over r. Well, we figured out what v was, right? That was 25.79 meters per second. So we square that, divide by the radius, which was 6.84 meters, right? So AC feet should be around like 97.2 meters per second squared. So we just take 125 minus 97.2, and that should give us like 27.8 meters per second squared there, because they're asking for the difference between the acceleration of his head and the acceleration due to, for his feet, right? So acceleration for his head, that was already determined in the problem that they were given, you know, they gave us that information to us. So they told us the maximum acceleration for the whole like arm and person was 12.5 g. So 12.5 times 10 meters per second squared, that's 125 meters per second squared. And then we're just looking for the centripetal acceleration for his feet, and we can figure that out by AC is equal to v squared over r. V is our linear speed that we figured out from part C, right? And our radius of curvature was from the arm pivot to his feet only. That's what we were concerned with. And then you just subtract the difference, like, so we figured out the difference between them. That is all. Makes sense for problem 9? Any questions about it at all? I know, Christian, you had a question about it. Did that clear everything up? Okay, cool. Other than problem 9, let's see here. I was thinking about going over specific. I mean, in general, this is a similar problem 5 here. Car coasts at a constant speed over a circular hill. Which of the free body diagrams to the right is correct? This is really similar to the written homework problem that we did. Well, if there's a circular pathway, we must have a centripetal acceleration and a centripetal force, right, pointing towards the center of the circle here. That is going to help keep us on that circular trajectory, right? So if we have a centripetal acceleration, right, if we are to have a acceleration towards the middle, right, a centripetal force, a net force towards the middle, then that force must be larger than the other forces on the same axis. So in this case, there's gravity and there's normal force, right? Normal force is the contact force, right, with the surface. Gravity is pulling us downward. So gravity has to be greater than normal force, right, in order to offer a net force in the negative y direction, in order to offer a negative acceleration, centripetal acceleration, pointed, so that's pointed downwards in the negative y direction towards the center of the circle. And then that gives us an overall centripetal force, right? Overall net force towards the center, keeping us along that circular trajectory. Now, another concept here is the fact that when you're looking at a circular motion, right, the direction of your velocity is going to be tangent to your curve. So if I'm curved this way and I'm looking at this point, then velocity is tangent to that. So my velocity direction would be this way, right? If I'm at the top of this curve here, my velocity vector is tangent to the curve. So tangent just means next to, right? immediately next to. So it would be horizontal like this, right? So that means if I were to let go, for example, like if I had a ball on a string that I'm just whipping around, around my head, right? If I were to cut that string or let go, then let's say if along a circle here, along that circular motion, for example, if I stopped here and I cut, actually, let me do this. So if I have this circle here, string, here's the ball, right? If I cut the string here, then what direction would the ball continue to move in? What's its velocity vector? You can kind of describe it if you just want to unmute and describe it. Nope. No one want to give it a shot? Yeah, no worries. I said if I cut the string here, right, and the ball is going to continue to move basically, right? So if I just cut it, like if I was, swinging around my head and I cut the rope all of a sudden, what direction is the ball going to move in? Like if it was moving this way, right, and I cut it at this instant when it was moving this way, how does it move? Yeah, I mean, well, yeah. Sorry, I wasn't like referring to like the car stuff, but yeah, you're absolutely right. It would be kind of that in that direction, right? Basically, it wouldn't be E because E, I mean, this way. I guess. Well, maybe I should have been more clear. Like if I was moving this way, basically, that's what I meant. And so if I cut the string while it was moving in that direction, then it would continue to kind of move tangent. Yeah, and if it was moving this way, then it would kind of move that way, basically. So yeah, just tangent to the curve in general. So dependent on if you were moving clockwise or counterclockwise, it would be either B or E, like relative to the other circle that I drew. Now, if we're talking about this example here, seen from above, a car rounds the curved path. Which vector represents the net force acting on the car? So if the car is maintaining a constant speed, right? Constant speed, so there's no like change in the magnitude of velocity, but there is acceleration that keeps us moving in that circular path. So net force has to be a result of the centripetal force because that's what's keeping us moving in a circular path. And so that centripetal force is pointing towards the middle, right? So in that case, if the car is maintaining constant speed, the net force acting on the car is our centripetal force, right? And that's pointed towards the middle, radially inward, and that's E, right? Now, if alternatively we have, if the car's speed increases, right? If the car's speed were to increase, then we would have an acceleration still pointed towards the middle. It's just not exactly like directly towards the center of the circle. It still point inwards, right? Because you're making that turn. A or C would be velocity vectors, basically, because they're tangent to the curve. B is like almost never an answer because this is just nothing here, really. Now, D is kind of a combination of both, right? So if I'm moving at a constant speed, centripetal acceleration pointed towards the center of the circle is what's going to keep me moving in that constant circular motion, right? Now, if I start speeding up, so there'd still be an acceleration towards the middle, right? Because I'm still making that turn. It still has to be pointing towards the middle. It's just that it might be at a different angle, basically. Does that make sense? And I think maybe if I try to explaining it using vectors, so like normally acceleration is equal to Vf minus Vi over t, right? And that's equal to delta V. If I think about this as vectors, right, Vf minus Vi, well, if I'm trying to go with a final velocity to the right, and I was moving with an initial velocity upwards, right? Because I'm making that turn, right? If I'm going north, I'm going to make a turn at an intersection to go east, for example, right? I have to make that turn. My final velocity is east. My initial was north, right? So if I do VF minus VI, well, VI is pointing upwards. So in order to subtract it from VF, I have to invert the direction. So you can see that delta V, right, which is pointed towards the middle, right? Like that, exactly radial inward. So delta V has to be the same direction as your acceleration. So in that case, if I, for example, were to speed up, right, if my velocity vector, my final velocity, was a lot larger, for example, I sped up, I went from VI that was 10 meters per second, for example, right? Let's say it was 10 meters per second to 60 meters per second, right? Then VI might be a lot smaller. And so in that case, then you can see that it's not exactly radially inward. It's more of an angle, because otherwise this would be like this. You can see that it's kind of more of an angle. So if I speed up, then my acceleration is still pointed towards the middle. It's just that it might not be exactly towards the middle of the circle exactly. So it'll point inwards to the circle, but not towards like the center necessarily. Does that make sense? Cool. Any other questions, like, that are bothering you guys about the online? Because we still have 15 minutes. I mean, we did problem 2. We did problems 5 and 6. 10, B, and C. Okay. Yep. So for 10, actually, I might as well just go through 10 entirely. So 10, fearless stuntman wants to clear a vertical loop on his bicycle. Figure shows a scenario where he clears his loop safely. That is without losing contact. Treat the Francisco plus bike system as a point mass in direct contact with a loop surface, and assume he stops pedaling before entering the loop, right? Ignore friction, other dissipative forces, and use G equals 10 meters per second squared. So the following are free body diagrams of the forces acting on Francisco at points 1 through 4 along the loop. Match each diagram to the correct point. So if we're at point 1, right, we have normal force acting upwards like this, and gravity pointing downwards, right? And since that is the case for 1, then this should be 1 right here. For 2, we have normal force this way and gravity straight downwards, right? Because normal force is going to be perpendicular to the surface of contact. If the surface of contact is the little ramp here, perpendicular to it makes a right angle with, normal force will be pointing to the right. So in that case, we can say that this one is 2. If we look at 3, normal force is pointing downwards here because surface of contact is like this, pushes up against the bicycle, right? That's downwards. And then we have gravity downwards as well, because gravity is always downwards, right? Then that means this should be 3. And then by process of elimination, this is 4, right? This is normal force like that, and gravity pointing downwards like this. That's A. B, it says to clear it safely, Francisco must be in contact with the loop at all times. Since he's most likely to lose contact at point 3, it is enough to ensure he's going at a sufficiently high speed to just avoid losing contact at this point. So, if the loop's radius is 2.5 meters, what is the minimum speed you should have at point 3? Express your answer in miles per hour. Note that this is not the speed at which you should approach the loop at point 1. You'll learn how to calculate that later on in the course. What is the magnitude of the normal force at point 3 at this minimum speed? So, if they're asking for the minimum speed at point 3, remember what I said earlier about the minimum speed, especially when you're on a loop-de-loop here? So if we have minimum speed at the top, if we go so slow we're going so slow to just avoid what? Exactly. So we're going slow enough to just preventing falling off or losing contact with the track, right? So that point where we're about to just lose contact is when we have what? Fn is equal to 0. Excellent. So we know that normal force is equal to 0 at that top point at 3, and that's just when the object is about, or the bicycle is about to lose contact with the track, and that's when you're going to have the lowest speed. You're going so slow or slow enough to the point that you're just barely going to lose contact with the track. So if Fn is equal to 0, we have a force here, right? Now we're trying to figure out speed. So think again, forces, speed, forces, right? Well, what force helps integrate speed? What force do we know integrates speed in its equation? Centripetal force, right? Because we know centripetal force is MAC, and that's mv squared over r, right? So we have a v there. So we want to relate normal force and the other forces that we know or we can calculate to what's it called? We want to relate normal force and centripetal force to speed, basically. So in that case, we can kind of set up a net force equation, right? So we have F net is equal to our centripetal force, and that's going to be pointing downwards, negative mv squared over r, because it's towards the center here, right? And then that's equal to negative Fn minus mg, right? Because Fn is pointing downwards, mg is pointing downwards as well, force of gravity. Now, Fn we already said is 0, so it doesn't matter. So we just have negative mv squared over r is equal to negative mg. Negatives cancel out, masses cancel out as well. So you're left with, once again, like I said earlier, it's a really common equation to get. You're going to be left with v is equal to root rg, right? Because we multiply over the r, right? And then take the square root. V squared, square root of that is v. Multiply the r over. We canceled out the negatives and the m's there already. So if we look at this, look at that, multiply over the r, v squared equals rg. Take the square root, v is equal to square root of rg, right? So this is our speed here. And we just take our radius, which was 2.5 meters, times our acceleration due to gravity, right? And so then we get our speed is just 5 meters per second, right? So all we have to do then is just convert it to miles per hour. And so, I mean, I don't want to go into like all the conversion factors for it, but there's, you know, however many miles in a meter, and then you convert seconds to minutes, or to hours basically, right? So hopefully you can figure out from 5 meters per second to miles per hour. But that's basically how to kind of set up the initial part of the problem. But C is, which of the following statements correctly describes Francisco's motion as he loops the loop? So A, executes a uniform circular motion. B, his tangential velocity vector is always perpendicular to acceleration vector. He moves with constant angular velocity. He moves with constant linear speed. His linear speed reaches a minimum at 0.3. So, okay, with uniform circular motion, right, we know the definition for uniform circular motion is traveling the same speed, right, all across that circular motion, right? So if he's entering that loop, right, with a certain speed, as they said in the problem, and he stops pedaling, well, stopping the pedaling is going to then result in a decrease in speed over a time interval, right? And so that means then that we're not going to see a constant speed over the entire time interval or over the entire circular path, right? And so that's even why we say here that we're looking for the minimum speed he should have at 0.3, right? I mean, he's going to go up there without pedaling, basically. And so there's going to be a decrease in speed over time. And so we want to make sure that, okay, well, there's supposed to be a minimum speed that he's going to travel with up till 0.3 that's going to keep him still in contact with the track. So considering the fact that he stops pedaling, right, his motion isn't uniform. Because he's slowing down on the way up, and he'll probably speed up on the way down, right? Because if he stops pedaling here, once he enters the loop-de-loop, right, he's going to go upwards. He's going to be affected or pulled down by gravity. Still going to go down here, and then he's going to speed up because gravity's going to pull him downwards a bit, right? Because he's not pedaling and maintaining a constant speed. So because there's no constant speed, he's not moving at uniform circular motion, right? And so for the idea of his tangential velocity vector is always perpendicular to his acceleration vector, well, acceleration is always pointing towards the middle, right? So the net force, right, the centripetal force, isn't always perpendicular to the velocity here. So if, for example, I guess we have 0.3, 0.3 might be this way, centripetal force that way, so that's perpendicular there, right? Now, here, might be pointing this way, but velocity is not quite perpendicular with it, for example. So, yeah, his tangential velocity vector isn't always perpendicular to the velocity. And so, his tangential velocity vector isn't perpendicular to the acceleration, that's what I meant. And then for C, he moves with constant angular velocity. I mean, this one is, I don't know if they really went over angular velocity in your lecture, but this is kind of extraneous. We're not going to be really concerned with this just yet. But we can also eliminate the fact that he moves with constant linear speed, right? Because he's going to be, like I said, he's not going to be pedaling all the way up or all the way down, so he's not maintaining a specific constant speed. And so he'll be slowing down on the way up, speeding up on the way down. And so we can eliminate the fact that he moves at a constant linear speed. But we know that from part B that his linear speed reaches a minimum at 0.3. So that should be the one that you have here. The constant angular velocity thing like that, I mean, that one's a little tricky because, like, you guys haven't really, at least I don't think you guys have gotten to angular velocity. Have you guys gotten to angular velocity? I'm not sure. Yeah. Have you guys gotten to that? Okay, then I'm not sure if I remember then. Okay. Yeah, I mean, the idea here is still the fact that, in a sense, your angular velocity is going to be dependent on, like, I see. So omega here is certain theta over time, right? You're covering certain portion of the circle in a period of time. Well, if theta, well, I guess, like, if you're not traveling the same speed, right, along the whole thing, right, then you're not going to be covering the same amount per time interval. Like, you're not going to be covering the same amount or distance around the circle in the same time interval. So you wouldn't have constant angular velocity in that case. And especially so because in terms of velocity, right, velocity is speed with a direction. And so, like, I don't know if you could really say in that case, like, since you're changing direction, it'd be a change in your, yeah, I guess you could say, since you're constantly changing direction, you're going to be changing your angular velocity. So based on that fact alone, changing direction would allow you to have a non-constant velocity, but maybe a constant speed if it was uniform circular motion. But since he's not pedaling, like I said, he's not maintaining a constant speed, he's just letting things go with the flow, right? He's not only having a non-constant velocity, but also a non-constant speed, because the speed is going to be changing. Like, the magnitude, the value is going to, he might go from 20 meters per second to 10 to 2, and then go speed it back up when he's going down to, you know, negative 10, negative 20, negative 30, whatever. But the idea is that he's changing direction and he's not moving at a constant, like, value, right? Because he's not pedaling. So that eliminates constant angular velocity, eliminates constant linear speed. Tangential velocity is not always perpendicular to acceleration, and it's not uniform circular motion because he's not covering the same distance every time interval. He's not moving at a constant speed, basically. But yeah, that's problem 10 as well. Does that make sense for problem 10? Cool. I think, yeah, it's 8 o'clock, so I think this is about the end of the session. We did 10, 9, 5, 6, 2, and yeah, I think that's it. 10, 9, 5, 6, 2. We covered 5 problems, so about half of the online homework, which isn't bad. I say that's pretty good. I mean, usually we never really did much with the online homework, if at all, with any of the other previous sessions. But like I said, if you guys have any questions about the other problems, just feel free to reach out, contact me. And yeah, I'll try to incorporate, maybe instead of like leaving you guys to kind of ask ones that you guys have trouble with, just because I feel like that might be a little bit slower, I might just kind of pull the ones that I feel like are really important, because then I'm covering, like, I know I'm covering important concepts. And then maybe if, like, you guys have any questions about anything else outside of those, we'll cover them as well. But yeah, that's pretty much the end of the session. I'm going to hit stop recording here. And yeah.